host for seminar on electron beam accelerator and infrared terahertz, free-electron lasers for strengthening frontier research ecosystem in Thailand. In the name of Thailand Center of Excellence in Physics, I would like to welcome our honorable guests and speakers for joining with us with the seminar today. การสัมมนาในครั้งนี้นะคะจัดขึ้นโดยวัตถุประสงค์เพื่อพัฒนาบุคลากรให้มีความเชี่ยวชาญด้านเครื่องเล่นอนุภาคและก็เทคโนโลยีที่เกี่ยวข้องกับการผลิตแล้วก็การประยุกต์ใช้รังสีอินฟราเรดและเทเลเฮิร์ตซ์นะคะแล้วก็สร้างเครือข่ายความร่วมมือระหว่างสถาบันและหน่วยงานวิจัยด้านเครื่องเล่นอนุภาคอิเล็กตรอนและเลเซอร์อิเล็กตรอนย่านอินฟราเรดและเทเลเฮิร์ตซ์ทั้งในและก็ต่างประเทศค่ะรวมไปถึงการขยายความร่วมมือกับสถาบันวิจัยศูนย์และก็ศูนย์วิจัยชั้นนำของโลกด้วยค่ะ This seminar is held by the purpose of improving personnel to be expert in electron beam accelerator and technologies of generating and utilizing infrared and terahertz free electron lasers, including building cooperation between institutions and research agencies which are working on electron beam accelerators, infrared terahertz free electron lasers, both inside and abroad, and strengthening the cooperation throughout world-leading research institutions. แล้วก็ในโอกาสนี้นะคะขอเรียนเชิญท่านรองศาสตราจารย์ดร.ดวงมณีว่องรัตนไพศาลผู้อำนวยการศูนย์ความเป็นเลิศทางฟิสิกส์ได้ให้เกียรติในการกล่าวต้อนรับผู้เข้าร่วมงานแล้วก็เปิดงานสัมมนาในครั้งนี้ค่ะ For this occasion, may I invite Assistant Professor Dr. ดวงมณีว่องรัตนไพศาล the Director of Thailand Center Excellence of Physics to deliver an opening speech for the seminar.
ค่ะสวัสดีค่ะนักวิจัยและอาจารย์ทุกท่านนะคะก็ช่วงแรกคงต้องดำเนินรายการเป็นภาษาอังกฤษเพราะว่าเดี๋ยวเรามีสปีกเกอร์เป็นอาจารย์จากญี่ปุ่นนะคะจากทั้งเกียวโตแล้วก็โทโฮกุนะคะในการร่วมสัมมนากับเราเช้านี้นะคะก็คงไม่ใช่ opening remark อะไรนะคะต้องขอบคุณอาจารย์ทุกท่านที่ให้เกียรติเข้ามาร่วมสัมมนาในวันนี้นะคะ Good morning everyone welcome to our seminar. This seminar is organized by Thailand Center of Excellence in Physics or TAPE Center and with the support of National Research Council of Thailand under the pilot hub of Talents for Electron Beam Accelerator and Infrared Terahertz Free Electron Laser for Strengthening Frontier Research Ecosystem in Thailand. Okay, I will move to the next slide with the objective of the project. Okay, we hope that today we are able to complete all these 5 objectives under your existing here. Okay, and actually the part and also the future for our collaboration. And I hope that these 5 objectives for this year we will be able to do it, and we cannot do it without you. Okay, so let all take advantage of this seminar or of this opportunity to grow and learn together. For this event, we have an exciting lineup of topics and activity for our morning. So let's make the most of it for this seminar. So let's all work together to create a welcoming and inclusive environment where our voices are heard and respected. So let's begin the journey of learning and discover together. Thank you for being here, and thank you all from Japan that who joined the conference at ICREM and be able to give some presentation at this seminar. Both Professor Sen and Professor Hama and all 3 speakers from Thailand side hope that this event will make us go together. After the talk, we can discuss and share. Thank you very much.
So ขอบพระคุณรองศาสตราจารย์ดร.ดวงมณีสำหรับการเปิดงานสัมมนาในครั้งนี้ด้วยนะคะในลำดับต่อไปนะคะจะขอต้อนรับทุกท่านเข้าสู่การบรรยายในหัวข้อการแนะนำการให้บริการด้านเลเซอร์อิเล็กตรอนอิสระด้านอินฟราเรดของมหาวิทยาลัยเกียวโตโดยศาสตราจารย์ดร. เฮอิชุนเซนจากหน่วยงานบริการด้านเลเซอร์อิเล็กตรอนอิสระย่านอินฟราเรดมหาวิทยาลัยเกียวโตประเทศญี่ปุ่นค่ะ On this occasion, may I welcome Professor Dr. Heishun Sen, a professor from Kyoto University Free-electron Laser, Kyoto University, Japan, to provide lecture on the topic of Introduction to Infrared Free-electron Laser Facility at Tokyo University. Please welcome Dr. Heishun Sen.
Thank you for kind introduction. I'm Heishun Zen from Kyoto University. I thought this is more closed, small meeting, so that my presentation is a little bit, how to say that, more specific one. And I start from the brief history of our facility development. The development itself was started from FL research in our institute is started by Professor Kiyoshi Yoshikawa in 1995, and the facility development was started by Professor Tetsuo Yamazaki in 1998, and I joined this group in 2003, around 20 years ago. So at the time I was very young, 20 years ago. And we obtained the first rating in 2008. So we took 10 years for the development to achieve the first rating on the mid-infrared free-electron laser. And after 2 months, we got the first FL saturation. And we started the external user program in 2011. And we started construction of the another source in the terahertz region in 2012. And we got the first right from this device in 2016. And recently we achieved the world highest conversion efficiency of the oscillator FL. This is the facility layout. Accelerator is concealed in the shielding blocks, shielding walls, and we have 2 accelerator-based infrared radiation sources. One is a mid-infrared free-electron laser, and another is a terahertz coherent undulator radiation. And the mid-infrared free-electron laser having the 3 user stations, user station 1, 2, 3. User station number 1 is for mid-infrared FL diagnostics and the simple irradiation experiment. And number 2 is for pump probe experiment station. We can combine the picosecond modeled laser amplified and the nanosecond YAG and the optical parametric oscillator. So we can perform the various experiments using the 4K cryocooler. It means that we can cool down the sample down to 4 Kelvin. And another source is the terahertz coherent undulator radiation. It covers the wavelength range from 600 to 1000 micrometer, 1 millimeter. And it have no user station. We should perform some experiment inside this accelerator room so that the availability of the light is a little bit less in this system. And we have homepage of this facility. If you're interested in, please check it. And we have 2 solid-state laser sources, as I mentioned, that the covering wavelengths is 1064, 532, and 666 nanometer for picosecond neodymium vanadate laser. And nanosecond neodymium YAG laser can produce 1064, 532, 355 to 66 nanometer, and also it can drive the nanosecond optical parametric oscillator, which covers the wavelength range from 410 to 710 and 710 to 2030, 300. And I moved to the introduction of the mid-infrared free-electron laser in our facility. This is the oscillator type free-electron laser driven by a normal conducting accelerator. And we use 4.5 cell microwave RF gun for generating the high energy and high charge electron beam. So the energy after the gun is 8.4 mega electron volt, and the total charge in the micropulse is 2.8 microcoulomb. And because the electron beam having the low energy component, a lot of low energy component, we should put slit to remove those unusable electron components. And after this energy selection section, the amount of electron is get to be 700 nanocoulomb per micropulse. Then we further accelerate the electron beam to the up to 40 MeV, keeping the total charge, and we made the electron bunch compression in here to compress the electron longitudinal length to be less than 1 picosecond, and injected it to the 8.8 meter undulator for undulator radiation generation, and we use 5.04 meter optical cavity for FA ranging. This is the performance, one of the representative graph for showing the performance of our FL. We can cover the wavelength from 3.4 micrometer to 25 micrometer. The intensity of the FL is strongly dependent on the wavelength, and we can have the maximum micropulse energy around 80 millijoule at 8.2 micrometer. And we can also extend to a little bit shorter wavelengths using second harmonic generation from 6 micrometer to 3 micrometer, or 5 micrometer to 2.5 micrometer. And I moved to the terahertz coherent undulator radiation source. This is the schematic image or the 3D image of the system. And for developing this facility or the source, two Thai students greatly contributed. One is the Shikarin Spako, and another is the Syrian Kurainara. And we generate a little bit higher bunch charge electron beam from the photocathode RF gun, and compress the electron bunch length in this tiny skein and inject it to the undulator. And the quasi-monochromatic coherent radiation is generated in the undulator when the electron bunch length is shorter than the radiation wavelength. And this is the result of the frequency or the spectral characterization. We constructed a microwave interferometer to measure the spectrum, and this is the interferogram, and by performing the Fourier transformation, we get spectrum of the radiation as like this, and we confirm the tuning of the wavelength and the bandwidth of the radiation. So, as you can see here, the monochromatic radiation generated in the frequency tunability is from 160 to 650 gigahertz. And the 10-cycle interference indicates the 10-cycle radiation. And then we measure the absolute energy and peak power of this source in the as a function of the electron bunch charge or total electron amount inside in the one bunch. And as you can see, up to some point, it follows the square law and depart in some point. This is due to the space charge effect. If the electron bunch charge get increased, then the electron bunch cannot be as short as a low charge condition. And we get the maximum micropulse energy around 1.3 microjoule at 0.16 terahertz, 160 gigahertz, and the highest peak power was 38 kilowatt at 330 gigahertz. And the peak power was calculated with assuming the 10 cycle radiation. And we also have the a bit exotic application of this facility. We provide a single electron irradiation environment to the user who want to characterize a scintillation material. So by reducing the electron emission from the gun and defocusing the electron beam and use a small collimator, we can provide a single electron irradiation apparatus in this section. So we change the energy of the electron beam and measure the pulse height of the scintillation material. And then we confirm the linear dependence of the pulse height on the electron beam energy. And then I moved a little bit the statistics of our facility. This is a history of external users and their main field. We started the external user program in 2011, and at that time the number of users is 3. And after 10 years here. After 8 years, the number of users increased up to 15 or 16 or 17. And this year we had 17 users, and distributed to material science, biology, and laser processing, and direct usage of electron beam. This is a single electron application, and the accelerator and the light source development research. And this is the number of published peer-reviewed paper from this facility. And as you can see, up to 2010, we only have having our activity. And after starting the user program, the application and the single electron related papers are increased. So in recent 4 years, there are more than 15 users, but the number of published papers is less than 15. So that the number of paper divided by number of users is less than 1. And but fortunately, we get 7 external users having the research budget from next to a private company. And some users can have good results in only 1 year experiment, but some users cannot have good results even in several user time. So that the research outcome is strongly depending on the user and the subject, so that we should be patient and support the users. And some users, another aspect, some users have enough data for writing several papers, but they have not had a published paper. So this is also a big problem, but we should also be patient. Just we can encourage them for us and the user side to get more budget and funding. So, and this is a schedule of our facility, so that we started from the beginning user experiments from beginning of June and end up that in the end of November. So this is a schedule booked, and red means I'm not in the facility, so that the facility cannot be operated. I'm the only person can operate the facility. This is also the big problem. And green means national holidays. There are some vacant slots, but in this season, most of the time the user come to make experiment and go back. and the schedule was constructed according to the user request. And day by day change, sometimes user only perform one day experiment and another day doing different experiment. So this is very tough for facility side, but I hope or I believe this is good for maximizing the user outcome. So, and that's all from me.
And I have one question. In your slide, you say like in experiment you have one electron. Is that for single electron irradiation condition?
This one,
Yeah.
we provided the single electron radiation condition for users, and we get limited energy. So we can provide from 1 eV, 1 mega electron volt to 6 mega electron volt. Lower energy I cannot. This is the actual spectrum or falsified spectrum of the scintillation material. So that this isolated peak indicates the irradiation of the single electron at the time. And if we increase the number of electrons, we can have another peak at the double to falsified. This means two electron irradiation or pilot, just pilot of two events. So we can confirm this is a true single electron event.
It's not in terms of probability. It's just only one single electron.
It depends. So that if we want to have more events, the probability distribution, this is the kind of Poisson distribution. And if we set the maximum peak of the Poisson distribution onto 1, so we also have 2 and 3 events. But we can take out the event which corresponds to the single electron event. So that is a kind of trick.
Okay, thank you very much.
Can you give us some more details of the what kind of material science project work at your facility?
So most of the material science is using this illustration number 2 and combine the solid state laser together with FL. And some users excited state by mid-infrared Free-electron laser as a pump to derive some excitation level, and probe it by the external laser or solid state laser. So we perform Raman spectroscopy. We excite some specific vibration mode by the infrared Free-electron. The vibrational mode of the material lies on the mid-infrared state wavelengths. And then we can measure the population, the vibrational state by using Raman scattering. Or we can initiate another optical or electrical change of this state of the material by FL and measure with some another means. And also another usage of we can pump the excite the material by the solid state laser. We use the ultraviolet to excite the carrier inside the material. And the mid-infrared can be used for probing the density of the carrier. And by measuring the time-dependent transmittance, we can evaluate the lifetime of the carrier inside the solid state or the semiconductor material or insulating material. That is most of the material scientists doing this process.
So like so how is these how are these how do these techniques like why is it better than the commercial Raman or the commercial like PL lifetime? Because like for our lab we use the PL lifetime to do the lifetime and look at all this like the carrier and commercial Raman as well. So like what is the benefits extra benefits?
Okay. Farmers and the user said there is a state having no radiative decay. Here can measure the lifetime of the radiative decay. It can emit light when the electron decays out from the excited state. But if the excited state have no vibration, radiative decay, no emission, but the electron decays, then the PM cannot measure. So the user found such kind of material, and that is very difficult to characterize the state itself and also the decaying time constant. So if we combine a little bit strong and monochromatic infrared together with short pulse pumping, we can measure the variation of the population at that state have no radiative decay by measuring the absorption or transmittance of the material. That he said this is very unique, and he is now preparing a paper for the publication, I hope.
Very much. What kind of sample, like it should be free or it should be single crystal or it can be liquid to do this experiment?
Most of the time users are using the single crystal. But using the 4K crystal, like uran, the material better to be solid, and I'm also sure but in case of powder or some the polycrystal, maybe the defect play a lot of role. So pure material response is given by a defect. Or someone wants to study the defects. So in that case, a lot of defect is accepted. Our user want to characterize a single crystal, but we may can use this for another kind of sample, but no trial.
Thank you very much, Professor Sen. So just a quick question about your cryostat. What are the dimensions, and can you attach electrical wires onto the sample? Let's say if I were to study optoelectronic properties under the mid-IR irradiation.
The dimension of the sample cell sample holding is 1/2 centimeter, and now we only have the optical windows, and we can possibly attach some heat loop to the vacuum. And I'm not so familiar about the wire bonding, but possibly we can do something about what you mentioned.
I see. Thank you very much.
Does anyone have any more questions? So please give a